Tonight is the night. December 19th, 2025. Right now, as you listen to these words, an object from another star system is making its closest approach to Earth. 168 million miles away, hurtling through the darkness at over 130,000 miles per hour, something ancient, something mysterious, something that has travelled for billions of years across the void between stars is passing us by. And after tonight, it will never return. This is not science fiction. This is happening right now. Welcome to a very special episode. Tonight we are not just covering the latest news about 3I-ATLAS. Tonight we are witnessing history. We're going to take you on a journey from this extraordinary moment all the way back to the night everything changed. Through every discovery, every anomaly, every impossible coincidence that has made 3I-ATLAS the most controversial and captivating cosmic visitor in human history. By the time we reach the end of tonight's story, you will understand why some scientists believe this object might be older than our own solar system. You will learn about the 15 anomalies that have left researchers divided and arguing in ways we have not seen since the discovery of Oumuamua. You will hear about a connection to a mysterious signal detected in 1977 that defies statistical probability. And you will discover what happens next as 3I-ATLAS continues its journey toward Jupiter, toward a rendezvous that some believe was planned. But first, let us be present in this moment. Let us honour what is happening right now, on this December night, under these winter stars, at approximately 600 hours, Universal Time on December 19th, 2025. An object designated 3I-ATLAS, also known by its formal name C2025-N1, reached its closest point to our planet. The distance, 1.798 astronomical units. In more familiar terms, roughly 270 million kilometres, or 168 million miles. That is nearly twice the distance between Earth and the Sun, yet this is as close as this interstellar wanderer will ever come to the world we call home. Think about that for a moment. An object that has been drifting through the emptiness between stars, possibly for 7 to 14 billion years, has finally arrived at our doorstep. Not to stay, not to collide, not to deliver any message we can easily decode, simply to pass through, to sweep past our star and our planets, and then to vanish back into the cosmic night from which it came. There is something almost unbearably poignant about that, like a ship passing in the night, like a stranger on a train who catches your eye, holds your gaze for one electric moment, and then is gone forever. But 3I-ATLAS is no ordinary stranger. Since its discovery on July 1st of this year, it has defied explanation at every turn. It has behaved in ways that comets should not behave. It has displayed characteristics that have never been observed in any object, interstellar or otherwise, and it has sparked a scientific controversy that has divided the astronomical community into camps that grow more entrenched with each passing week. Let us talk about what we're seeing right now. In the hours surrounding closest approach, telescopes around the world have been trained on 3I-ATLAS. The Virtual Telescope project in Italy hosted a live stream, though rain initially delayed observations. Amateur astronomers across the globe have been capturing images, contributing to a collective portrait of this mysterious visitor. But the most extraordinary observations have come from space itself. Just yesterday, NASA released images captured by the Europa Clipper spacecraft. This is the probe currently en route to Jupiter's moon Europa, where it will search for signs of life beneath the ice. But before it reaches its destination, Europa Clipper found itself in a unique position to observe 3I-ATLAS. On November 6th, 2025, Europa Clipper's ultraviolet spectrograph instrument spent 7 hours watching the interstellar comet from a distance of approximately 102 million miles. At that time, Earth-based observations were largely blocked by the Sun's position. The view from Europa Clipper was quite literally irreplaceable. What did it see? The instrument detected signatures of oxygen, hydrogen, and dust streaming from 3I-ATLAS. The spacecraft observed the comet from a sunward direction, giving scientists a unique downstream view of both the dust tail and the plasma tail. This perspective revealed details about the comet's outgassing that would have been impossible to capture from Earth. Dr. Kurt Rutherford, the principal investigator for the Europa ultraviolet spectrograph, called the opportunity completely unexpected. His team can see gases coming off the comet and water molecules breaking apart into hydrogen and oxygen atoms. This capability provides a deeper view into the comet's processes and composition. But Europa Clipper was not the only spacecraft watching. In late November and early December, X-ray telescopes turned their attention to 3I-ATLAS, and what they found was unprecedented. Japan's X-ISM Observatory, a joint mission with NASA and the European Space Agency, observed 3I-ATLAS between November the 26th and 28th for 17 hours. The images revealed something extraordinary, a halo of X-ray emission extending approximately 250,000 miles from the comet's nucleus. That distance is roughly equal to the separation between Earth and the Moon. This X-ray glow was not coming from the comet itself. Comets are far too cold to emit X-rays thermally. Instead, the emission results from a process called charge exchange. When highly charged ions in the solar wind, such as oxygen and carbon ions stripped of many electrons, collide with neutral gas molecules released by the comet, they capture electrons. As these ions relax to lower energy states, they emit photons in the X-ray band. This mechanism has been observed in dozens of comets within our own solar system, but 3I-ATLAS is not from our solar system. It is the first interstellar comet ever observed in X-ray light. Then came the European Space Agency's XMM Newton Observatory. On December 3, 2025, XMM Newton spent 20 hours observing 3I-ATLAS from a distance of roughly 175 to 177 million miles. The resulting image shows the comet glowing in low-energy X-rays, a vivid red beacon against the darkness of space, surrounded by fainter gradients of purple and blue. The X-ray data is particularly valuable because it can detect gases that other instruments miss. While optical telescopes see dust and certain gas species, and infrared instruments trace molecules like water and carbon dioxide, X-ray observations are uniquely sensitive to hydrogen and nitrogen. These are elements that have been difficult to study through other wavelengths. What all of this tells us is that 3I-ATLAS is actively outgassing. It is shedding material into space at a significant rate. The sun's heat is sublimating its ices, just as it does with comets born in our own solar system. And yet, something is different. Look at the images carefully. 3I-ATLAS displays what astronomers call an anti-tail. Most comets have tails that point away from the sun, pushed by solar radiation pressure and the solar wind. But 3I-ATLAS has a prominent feature pointing toward the sun. This sunward jet has been visible since the very first Hubble Space Telescope images captured in July. Harvard astrophysicist Avi Loeb has written extensively about this phenomenon. He notes that the anti-tail was apparent in the first Hubble image, taken on July 21st, when 3I-ATLAS was approaching the sun from a distance of nearly 3 astronomical units. It remained visible in the second Hubble image, taken on November the 30th, when the comet was receding away from the sun. The persistence of this feature is, in Loeb's words, a mystery. Gas and micrometer-sized dust particles should be pushed away from the sun by solar radiation pressure. They should not form a prominent, tightly collimated jet pointing sunward. Loeb has proposed several explanations. In papers authored with Eric Quito, he suggests the anti-tail might result from the scattering of sunlight by tiny ice fragments shed from the sun facing side of 3I-ATLAS. These particles would evaporate before being pushed back by solar radiation. Another paper, published on December the 8th, associates the anti-tail with a swarm of objects lagging behind 3I-ATLAS due to its non-gravitational acceleration. Non-gravitational acceleration. That phrase has become central to the controversy surrounding 3I-ATLAS. It refers to motion that cannot be explained by gravity alone. Something is pushing this object, and the question of what that something might be has ignited a firestorm of speculation. For most comets, non-gravitational acceleration is explained by outgassing. As ices sublimate and jets of gas erupt from the surface, they act like tiny rocket engines, nudging the comet off its purely gravitational path. This is well understood. This is normal. But nothing about 3I-ATLAS has been normal. The mainstream astronomical community insists that 3I-ATLAS is a comet. NASA officials stated as much in their press conference on November 19th. The object has a coma, it has a tail, It is outgassing volatiles like carbon dioxide, water, carbon monoxide, and hydrogen cyanide. By every conventional measure, it walks like a comet and quacks like a comet. Yet the anomalies keep accumulating. The anti-tail that should not exist. The extreme negative polarization unprecedented among all known comets. The nickel to iron ratio that resembles industrial alloys more than natural celestial bodies. The trajectory aligned with the ecliptic plane to within 5 degrees. The arrival direction coinciding with the WOW signal from 1977. These are not minor curiosities. These are statistical improbabilities stacked upon statistical improbabilities. And tonight, as 3I-ATLAS reaches its closest approach to Earth, we find ourselves at a crossroads. We can accept the conventional explanation and move on, or we can ask the questions that science demands we ask when confronted with phenomena that defy our expectations. What is 3I-ATLAS? Where did it come from? Why does it behave the way it does? And perhaps most haunting of all, is it merely passing through, or is it here for a reason? The answers may lie in the story of its discovery. On a winter night 6 months ago, telescopes in Chile detected a faint smudge of light moving against the background stars. No one knew then what they had found. No one could have imagined the journey that lay ahead. Let us go back to the beginning. Let us return to July 1st, 2025, to the moment when humanity first glimpsed its third confirmed visitor from beyond the solar system. Because to understand where 3I-ATLAS is going, we must first understand where it has been and the trail of mysteries it has left in its wake. July 1st. The night. Everything changed. The Atlas telescope at Rio Hurtado, Chile, sits at an elevation of nearly 5,000 feet in the Atacama Desert, one of the driest places on Earth. The skies here are so clear, so dark, so free of light pollution that astronomers sometimes say you can see the universe breathing. On the night of July 1st, 2025, those pristine skies revealed something that would change everything. ATLAS stands for Asteroid Terrestrial Impact Last Alert System. It is a NASA-funded network of telescopes designed to scan the heavens for objects that might pose a threat to our planet. Every night, these robotic sentinels photograph vast swathes of sky, and sophisticated software compares each new image against previous observations, looking for anything that has moved. On that July night, the software flagged an anomaly. A faint smudge of light at apparent magnitude 18, far too dim to see with the naked eye, was drifting through the constellation Serpens Cauda, near the border with Sagittarius. This region of sky lies close to the galactic plane, where the dense star fields of the Milky Way's centre create a cosmic backdrop so crowded that detecting small moving objects becomes extraordinarily difficult. Perhaps that is why it took so long to notice. Sam Dean, an amateur astronomer who would later comb through archival data, found evidence that ATLAS had actually been imaging the object since at least June 5th, 20 days before the official discovery. The Zwicky Transient Facility at Palomar Observatory had captured it even earlier, with observations dating back to June 14th. But on July 1st, the object crossed a threshold. The software determined with sufficient confidence that this was something new, something worthy of human attention. A report was filed with the Minor Planet Center, the international clearinghouse for astronomical discoveries. Within hours, the initial excitement gave way to something far more profound. As astronomers around the world began calculating the object's trajectory, a startling picture emerged. This was not an ordinary asteroid. This was not a comet from our own Oort cloud. The mathematics were unambiguous. Whatever this object was, it was moving too fast and on too steep a trajectory to have originated within our solar system. The velocity sealed the case. 3I-ATLAS was screaming through the inner solar system at approximately 61 kilometers per second relative to the Sun. That translates to roughly 136,000 miles per hour. No gravitational slingshot from any planet could have accelerated an object born in our solar system to such speeds. This thing had come from somewhere else. By the end of that first week in July, the designation was official. The International Astronomical Union assigned it the name 3I-ATLAS, with the 3I prefix indicating that it was the third confirmed interstellar object ever detected, following Oumuamua in 2017 and Borisov in 2019. The Atlas portion honoured the telescope system that made the discovery. But what kind of object was it? This question sparked immediate debate. The initial observations were ambiguous. 3I-ATLAS appeared point-like in most images, consistent with either an asteroid or an inactive comet. But there were subtle hints that something more complex might be happening. The object seemed slightly fuzzy around the edges, as if surrounded by a faint haze. Within days, larger telescopes turned their attention to the newcomer, and on July 21st, the Hubble Space Telescope captured an image that eliminated any doubt about 3I-ATLAS being an active body. The Hubble image revealed a teardrop-shaped cocoon of dust streaming away from a solid, icy nucleus. This was a coma, the characteristic halo of gas and debris that forms when solar heating causes a comet's frozen volatiles to sublimate directly into space. 3I-ATLAS was not a dead rock tumbling through the void. It was alive, geologically speaking, actively shedding material as it fell toward our sun. But the Hubble image revealed something else, something that would become the first of many puzzles. Even at this early stage, there was a hint of material extending toward the sun, not away from it. The anti-tail that would later become so prominent was already beginning to form. Astronomers rushed to characterize the object. How big was it? How massive? What was it made of? These size estimates proved challenging. Because we cannot directly resolve the nucleus, scientists must infer its dimensions from brightness measurements and assumptions about reflectivity. Early calculations suggested a diameter somewhere between 440 meters and 5.6 kilometers. The uncertainty was enormous, spanning more than an order of magnitude. If the larger estimate is correct, 3I-ATLAS would be substantially bigger than either of its interstellar predecessors. Oumuamua measured perhaps 200 meters in its longest dimension, while Borisov's nucleus was estimated at around 1 kilometer. A 5-kilometer 3I-ATLAS would make it a true giant among interstellar visitors. The mass estimates were equally staggering. Some calculations suggested the object could weigh more than 33 billion tons. To put that in perspective, that is roughly 1 million times more massive than Oumuamua. Whatever ejected 3I-ATLAS from its home system had flung an enormous amount of material into the void between stars. But where had it come from? This question led researchers into the realm of galactic archaeology. By analysing the object's velocity components, astronomers could trace its journey backward through space. The results pointed toward the constellation Sagittarius, in the general direction of the Milky Way's centre. But 3I-ATLAS had not come from the galactic core itself. Its trajectory suggested an origin in a region of space that most of us rarely consider. Our galaxy is not a simple disk of stars. It has structure, layers, populations that differ in age and composition. The thin disk, where our sun resides, contains relatively young stars, typically less than 10 billion years old. But sandwiching this thin disk is another structure called the thick disk, a population of ancient stars that orbit above and below the galactic plane. The thick disk is old, very old. Stars in this region formed when the universe itself was young, typically 7 to 12 billion years ago, long before our own solar system coalesced from its primordial cloud of gas and dust. And the trajectory of 3I-ATLAS suggested it might have come from this ancient population. Matthew Hopkins, an astronomer at the University of Oxford, had been developing models to predict the properties of interstellar objects based on their likely stellar origins. Just a week before 3I-ATLAS was discovered, Hopkins had defended his doctoral thesis on this very topic. When the news broke, he found himself in a unique position to test his predictions against reality. Hopkins' analysis was remarkable. Using a statistical model called the Otautehe-Oxford model, he and his colleagues estimated that there was roughly a 2/3 probability that 3I-ATLAS was older than our solar system. Their best estimate placed the object's age somewhere between 7.6 and 14 billion years. Think about what that means. If Hopkins is correct, 3I-ATLAS formed around a star that ignited when the universe was less than half its current age. It was ejected from that system, perhaps during the violent rearrangement of young planets, and it has been drifting through the galaxy ever since. For billions of years, this frozen wanderer has sailed through the darkness, passing countless stars, witnessing the birth and death of solar systems, carrying within its ancient ice a record of conditions that existed before Earth, before the Sun, before anything we know. Professor Chris Lintott, co-author of the study and presenter of the BBC's Sky at Night programme, summarised the implications elegantly. This is an object from a part of the galaxy we have never seen up close before. We think there is a 2/3 chance this comet is older than the solar system, and that it has been drifting through interstellar space ever since. The chemistry of 3I-ATLAS seemed to support this ancient origin. Cosmic ray bombardment over billions of years would transform surface ices, producing carbon dioxide-rich crusts and darkened, irradiated layers. And indeed, observations by the James Webb Space Telescope in August revealed unusually high ratios of carbon dioxide relative to water, consistent with exactly this kind of long-term cosmic ray processing. But age was not the only remarkable aspect of the object's origin. There was also the matter of its arrival direction. 3I-ATLAS came from the south. This might seem like a trivial detail, but it was actually quite unexpected. Astronomers had predicted that most interstellar objects should appear to come from the direction of the solar apex, the point in the sky toward which the Sun is moving relative to nearby stars. This direction lies in the northern celestial hemisphere, near the constellation Hercules. Instead, 3I-ATLAS arrived from almost the opposite direction. It came from the south, from Sagittarius, from near the galactic centre. This southern origin made it harder to detect and challenged assumptions about how interstellar objects should behave. The speed was also notable. 3I-ATLAS was moving faster than either Oumuamua or Borisov, yet this velocity was consistent with predictions for objects from the thick disk population. The high speed was not evidence of anything unusual. It was simply what one would expect from an ancient wanderer that had been kicked around by gravitational encounters with other stars over billions of years. In those early weeks after discovery, there was hope that we might trace 3I-ATLAS back to its specific parent star. Researchers scoured the Gaia database, which contains precise positions and motions for billions of stars in our galaxy. A team led by Yiang Guo found that 3I-ATLAS may have passed within 1 parsec, about 3.3 light-years, of 25 known stars in the past 10 million years. But 10 million years is nothing on cosmic timescales. 3I-ATLAS has likely been travelling for billions of years. During that time, it would have been mixed and stirred by countless stellar encounters, its original trajectory scrambled beyond recognition. We will never know which star gave birth to this cosmic orphan. We can only study what it has become. As July gave way to August, the observational campaign intensified. Ground-based telescopes across the globe trained their optics on the visitor. Space telescopes carved out precious observing time, and researchers began detecting something that would deepen the mystery considerably. 3I-ATLAS was outgassing, and the composition of that outgassing was not entirely normal. The James Webb Space Telescope observed the comet on August 6th using its near-infrared spectrograph. The data revealed signatures of carbon dioxide, carbon monoxide, water ice, and a compound called carbonyl sulfide. The carbon dioxide to water ratio was significantly elevated compared to most solar system comets. This could be explained by the object's ancient origin. Billions of years of cosmic ray bombardment would convert carbon monoxide ice into carbon dioxide. The chemistry was consistent with extreme age. But there were other detections that proved harder to explain. Spectroscopic observations revealed the presence of atomic nickel in the coma. Nickel had been detected in solar system comets before, so this was not unprecedented. What was unprecedented was the ratio of nickel to other elements. 3I-ATLAS appeared to contain much more nickel than iron. In most natural settings, nickel and iron appear together in predictable proportions. But in 3I-ATLAS, the nickel dominated. The nickel to cyanide ratio was orders of magnitude larger than in thousands of known comets, including the previous interstellar visitor, Borisov. This anomaly caught the attention of Avi Loeb. The Harvard astrophysicist had already achieved notoriety for his controversial suggestions that Oumuamua might have been an alien artifact. Now he was turning his analytical eye toward 3I-ATLAS, and he did not like what the nickel data implied. Loeb pointed out that the nickel without iron signature resembles what one finds in industrially produced nickel alloys. On Earth, the carbonyl process is used to refine nickel and separate it from iron. The result is high-purity nickel with minimal iron contamination. Was this evidence of artificial processing? Loeb was careful not to make definitive claims. But he added this observation to a growing list of anomalies that he felt deserved serious consideration. The mainstream astronomical community pushed back. There could be natural explanations for unusual metal ratios. Perhaps the parent star of 3I-ATLAS was itself unusual, depleted in iron relative to nickel. Perhaps some unknown process during the comet's formation had concentrated nickel preferentially. The data was limited, the uncertainties were large, and extraordinary claims required extraordinary evidence. But the anomalies kept coming, and by the time 3I-ATLAS disappeared behind the Sun in late October, on its way to perihelion, the list of puzzling observations had grown long enough to fuel a controversy that shows no signs of abating. In those summer months of 2025, humanity had its first extended look at a visitor from another star. What we saw was beautiful, mysterious, and deeply strange. An ancient wanderer, possibly older than our own world, shedding its primordial ices into the warmth of an unfamiliar sun, carrying secrets we're only beginning to decode. But the real surprises were still to come. As 3I-ATLAS rounded the Sun and emerged back into view, it would reveal behaviours that stretched the definition of cometary activity. Jets pointing the wrong direction, polarisation patterns never before observed, and a trajectory that seemed almost too perfect to be coincidental. The summer of discovery was ending. The autumn of anomalies was about to begin. 7 billion years. In the making, the ancient traveller from the thick disk. Close your eyes for a moment and try to imagine 7 billion years. Not 7 billion miles, which is merely the distance to the outer planets. Not $7 billion, which wealthy nations spend in days. 7 billion years. The span of time that may have passed since 3I-ATLAS was born. When this object first coalesced from the swirling disk of gas and dust around its parent star, Earth did not exist. Our Sun did not exist. The atoms that would one day form your body were still scattered across the galaxy, locked in the cores of stars that had not yet exploded, or drifting as sparse hydrogen in the endless void between stellar nurseries. The universe itself was barely half its current age. Galaxies were still merging, still taking their modern shapes. The Milky Way was a younger, more chaotic place, its spiral arms less defined, its stellar populations still sorting themselves into the thin disk and thick disk structures we observe today. And somewhere in that ancient cosmos, around a star that may have died billions of years ago, a small body of ice and rock and metal came together. It orbited its sun, perhaps for millions of years, perhaps for much longer. It witnessed whatever events unfolded in that distant system, events we will never know, around a star whose name we will never learn. Then something happened. A gravitational disturbance, perhaps the migration of giant planets, perhaps a close encounter with a passing star flung this small body out of its home system. It accelerated to escape velocity and kept going, breaking free from its parent star's gravitational embrace and sailing into the darkness between stars. And it has been falling ever since. Let us consider what the journey must have been like. Interstellar space is not truly empty, but it is close. The density of matter between stars is roughly 1 atom per cubic centimetre. For comparison, the air you are breathing contains about 25 quintillion molecules per cubic centimetre. The void between stars is a vacuum more perfect than anything we can create in our laboratories. Through this near-nothingness, 3I-ATLAS drifted. The temperature dropped to just a few degrees above absolute zero. Its surface ices, which may have been volatile when the object was young, froze solid and stayed frozen for eons. Cosmic rays, the high-energy particles that permeate interstellar space, bombarded its surface continuously, slowly transforming its chemistry, building up a processed crust many feet thick. Occasionally, 3I-ATLAS would pass near another star. Not close enough to be captured, but close enough to feel a gravitational tug. Each encounter would alter its trajectory slightly, like a billiard ball glancing off the cushion. Over billions of years, these accumulated deflections scrambled its original path so thoroughly that tracing it back to any specific origin star became impossible. The Gaia Space Observatory has mapped the positions and motions of nearly 2 billion stars in our galaxy. Researchers used this data to search for any star that 3I-ATLAS might have passed close to in the past 10 million years. They found 25 candidates, stars that came within about 3 light-years of the object's reconstructed path. But 10 million years represents only a tiny fraction of the object's total journey. If 3I-ATLAS is truly 7 billion years old, then 10 million years is just 1/700th of its lifetime. It would be like trying to determine where a person was born by examining only the last 2 weeks of a century-long life. The information simply is not there, so we cannot know where 3I-ATLAS came from, not with any specificity. But we can know something about the environment that produced it, and that knowledge is itself profound. The key evidence comes from the object's velocity through the galaxy. Astronomers describe stellar and object motions using 3 components, designated U, V, and W. U measures motion toward or away from the galactic center. V measures motion in the direction of galactic rotation. W measures motion perpendicular to the galactic plane, up or down. Most stars near the Sun have relatively small W velocities. They bob gently up and down through the thin disk, never straying far from the galactic plane. But 3I-ATLAS arrived with a W velocity of plus 18.5 kilometers per second relative to the Sun. This is unusually high. Such an elevated vertical velocity is characteristic of the thick disk population. These are stars, and presumably the debris around them, that follow tilted orbits, oscillating well above and below the main galactic plane, and critically the thick disk is old. Its stars formed early in the Milky Way's history, typically 7 to 12 billion years ago. The implication is striking. If 3I-ATLAS was ejected from a thick disk star system, then it formed around a star that was ancient even by astronomical standards. The object itself would have to be at least as old as that star system, and possibly older if it drifted for some time before being ejected. The Ototahi-Oxford model, developed by Matthew Hopkins and colleagues, uses statistical methods to estimate the likely ages of interstellar objects based on their trajectories. When they applied this model to 3I-ATLAS, the results suggested a most probable age range of 7.6 to 14 billion years. There was roughly a 2/3 probability that the object predated our solar system. Some analyses have pushed even further. A team led by Xavier Perez Couto at the University of A Coruña in Spain attempted to trace the object's path through the galaxy using simulations involving over 13 million stars. Their work suggested 3I-ATLAS could be around 10 billion years old. 10 billion years, a number so vast it becomes almost meaningless without context. Let me try to provide some. 10 billion years ago, the universe was only 3.8 billion years old, less than 30% of its current age. The cosmic microwave background radiation, the afterglow of the Big Bang, was not much cooler than it is today, but the universe looked very different. Large-scale structures were still forming. Many of the galaxies we observe now did not yet exist in their present forms. In our own Milky Way, the thick disk was still actively forming. Stars were being born at a prodigious rate, enriching the interstellar medium with heavy elements forged in their cores and scattered by supernovae. The conditions were right for the formation of planetary systems, though these early systems would have been somewhat different from our own, built from material with lower concentrations of the heaviest elements. 3I-ATLAS may be a remnant from one of those primordial systems, a frozen time capsule preserving within its ancient ices a chemical record of conditions that existed before our corner of the galaxy had even begun to take shape. The chemistry detected by the James Webb Space Telescope seems consistent with this picture. 3I-ATLAS shows elevated ratios of carbon dioxide to water compared to most solar system comets. This could result from cosmic ray processing over billions of years. The incoming particles would have slowly transformed carbon monoxide ice into carbon dioxide, building up a distinctive chemical signature of extreme age. The object's surface also shows evidence of irradiation. Observations have suggested a reddish colour in some wavelengths, consistent with the presence of tholins, complex organic molecules produced when simple ices are bombarded by radiation over long periods. Tholins are found on many outer solar system objects, but the specific composition and distribution on 3I-ATLAS may reflect billions of years of cosmic ray exposure rather than mere millions. There is something almost sacred about this. We are looking at material that has remained essentially unchanged since before our sun ignited. The atoms in 3I-ATLAS were assembled around an alien star, in an alien system, under conditions we can only imagine. They have travelled distances that dwarf anything in human experience, crossing voids so empty that the object might have gone millions of years between encounters with even a single stray atom. And now, briefly, impossibly, this ancient traveller has entered our realm. It is passing through our solar system, shedding some of its primordial material into our sun's warmth, revealing secrets it has kept for longer than Earth has existed. But the age of 3I-ATLAS is not merely a matter of wonder. It also raises questions about what else the object might carry. Consider the implications of a 10 billion year journey. Over such timescales, even extraordinarily unlikely events become possible. A comet drifting through the galaxy would occasionally pass through molecular clouds, regions of space where gas and dust concentrate. It would be subject to whatever environmental conditions existed at various points in galactic history. It might even pass close enough to other planetary systems to pick up material ejected from those worlds. What if 3I-ATLAS carries traces of multiple stellar systems? What if its ices contain isotopic signatures from different environments, different epochs, different regions of the galaxy? A detailed analysis of the object's composition could reveal not just the conditions in its birth system, but information about its entire voyage across space and time. We do not yet have such detailed data. 3I-ATLAS is too far away, and our observation window too brief to extract such subtle information. But the possibility tantalizes researchers. This object is not merely a comet from another star. It is potentially a geological sample from across the Milky Way, a core drilled through billions of years of galactic history. And there is another implication of the object's extreme age, one that touches on questions far beyond geology. If 3I-ATLAS is 7 to 14 billion years old, then it formed in an era when the universe was already billions of years old. Enough time had passed for multiple generations of stars to live and die, enriching the cosmos with heavy elements. Enough time for rocky planets to form. Enough time, perhaps, for life to arise. We have no evidence that 3I-ATLAS is anything other than a natural comet. The mainstream scientific consensus holds firmly that it is exactly what it appears to be. An icy body from another solar system, remarkable primarily for its origin and its age. The anomalies that have excited so much speculation likely have natural explanations that we simply have not yet identified. But Avi Loeb and others have argued that we should keep an open mind. If intelligent life arose elsewhere in the galaxy billions of years ago, such civilizations would have had ample time to explore, to expand, to send probes to other star systems. Some of those probes might be indistinguishable from natural objects at first glance. Loeb is careful to note that he is not claiming 3I-ATLAS is artificial. He estimates the probability at perhaps 40%, leaving the majority of likelihood on the side of natural origins. But he argues that the object's anomalies warrant serious investigation, that dismissing the possibility of artificiality without thorough examination would be unscientific. The mainstream community has largely rejected this framing. Professor Jason Wright of Penn State University has published detailed rebuttals of Loeb's claimed anomalies, arguing that each can be explained by natural processes or results from misinterpretation of the data. The scientific establishment remains confident that 3I-ATLAS is a comet, albeit an unusual one. This debate will not be settled by rhetoric. It will be settled by data. And while 3I-ATLAS remains within range of our telescopes, every observation brings us closer to understanding what this ancient visitor truly is. What we can say with confidence is this: whether natural or artificial, 3I-ATLAS represents something unprecedented. An object potentially older than our world, carrying ice formed before our sun ignited, shaped by billions of years of wandering through the cosmos. It is a messenger from the deep past, from a galaxy far younger than the one we know, from an epoch when the foundations of everything we see around us were still being laid. In a few years, 3I-ATLAS will fade from view, too distant and too dim for even our most powerful telescopes to track. It will continue its journey, sailing outward toward the stars, carrying its ancient secrets into another eternity of silence and cold. But for now, for this brief window, we can study it. We can analyze its light, model its trajectory, and piece together what fragments of its story are accessible to our instruments. Each observation is precious. Each data point is a word in a message that has taken billions of years to arrive. The ancient traveller is here. What else it might reveal depends on how carefully we are willing to look, and how open we remain to possibilities we have not yet imagined. The 15 anomalies that defied every explanation. Science progresses through anomalies. When observations contradict expectations, when data refuses to fit neatly into existing theories, that is when the most interesting questions emerge. It is in those gaps between prediction and reality that new understanding is born. 3I-ATLAS has given us more anomalies than any cometary object in memory. By some counts, the list has grown to 15 distinct features that challenge conventional explanations. Whether these anomalies point towards something exotic or merely reflect our incomplete understanding of interstellar comets remains the central question dividing the astronomical community. Let us walk through them systematically. Let us examine what has been observed, why it is considered unusual, and what explanations have been proposed. By the end, you will understand why this object has generated such fierce debate, and why some researchers believe we may be looking at something unprecedented in the history of astronomy. The first anomaly concerns trajectory. 3I-ATLAS follows a retrograde orbit, meaning it is travelling in the opposite direction to the planets as they circle the Sun. This alone is not remarkable. Roughly half of all comets from the outer solar system have retrograde orbits, but the specific orientation of 3I-ATLAS is striking. Its orbital plane is aligned with the ecliptic, the plane in which Earth and the other planets orbit, to within just 5 degrees. Random interstellar objects should arrive from all directions uniformly. The probability of such close alignment occurring by chance is roughly 0.2%, or about 1 in 500. Why would an interstellar object just happen to arrive aligned with our planetary plane? Loeb has suggested this might indicate a designed trajectory, chosen to facilitate observation of the planets or interaction with the inner solar system. Critics counter that we have only 3 interstellar objects to study, far too few to draw statistical conclusions. Perhaps we simply got lucky, or perhaps our detection methods favour objects with certain orbital orientations. The second anomaly involves timing. The arrival of 3I-ATLAS was precisely timed to bring it close to multiple planets, while rendering it unobservable from Earth during its closest approach to the Sun. The object passed within 29 million kilometres of Mars in early October, close enough for Mars orbiters to capture detailed observations. It will approach within 54 million kilometres of Jupiter in March 2026. Meanwhile, 3I-ATLAS reached perihelion on October 29th, when it was hidden behind the Sun from Earth's perspective. Solar conjunction occurred just 8 days before perihelion, blocking our view during the most active phase of the comet's journey. Loeb has calculated the probability of such a configuration occurring randomly at less than 0.005%. The fine-tuning appears almost too perfect to be coincidental. But critics note that this kind of reasoning can be misleading. Any specific configuration of events has low probability when calculated after the fact. If 3I-ATLAS had arrived at a different time, we could have calculated how unlikely that particular timing was as well. Without a prior prediction, these probability arguments lose much of their force. The third anomaly concerns mass. 3I-ATLAS is enormous by interstellar object standards. Its nucleus may be up to 5.6 kilometres across, with a mass potentially exceeding 33 billion tonnes. This makes it roughly 1 million times more massive than Oumuamua and 1,000 times more massive than Borisov, the 2 previous interstellar visitors. Such massive objects should be much rarer than smaller ones. The laws of planetary formation suggest that star systems should eject far more small debris than large debris. Finding such a giant as only our 3rd interstellar detection is statistically surprising. One explanation is that larger objects are simply easier to detect. Our surveys are biased toward finding bigger, brighter objects, so even if small interstellar visitors vastly outnumber large ones, we would preferentially discover the giants. This selection effect could explain the apparent anomaly without invoking anything unusual about 3I-ATLAS itself. The fourth anomaly involves chemical composition. As mentioned earlier, the coma of 3I-ATLAS contains nickel in unusual abundance relative to iron. In most natural settings, These elements appear together in predictable ratios reflecting their cosmic abundances, but 3I-ATLAS shows a nickel-to-iron ratio that resembles industrially processed nickel alloys. The nickel-to-cyanide ratio is also anomalous, orders of magnitude higher than in any of the thousands of comets previously studied, including the interstellar comet Borisov. Loeb has pointed out that this signature resembles what one would expect from technological processing. The carbonyl process used in industrial nickel production separates nickel from iron through chemical rather than physical means. Could 3I-ATLAS contain material that was artificially refined? Mainstream researchers are skeptical. The object's parent star may have had unusual elemental abundances. Unknown natural processes during the comet's formation might have concentrated nickel preferentially. The data uncertainties are substantial, and the detection of iron is difficult at the distances involved. More observations would be needed to confirm whether this anomaly is real or a measurement artifact. The fifth anomaly concerns the anti-tail. Most comets develop tails pointing away from the sun, pushed by solar radiation pressure and the solar wind. 3I-ATLAS displays a prominent jet pointing toward the sun, a feature that has persisted from the earliest Hubble observations through the present day. This sunward jet is tightly collimated, extending to within 8 degrees of the solar direction, out to distances of 500,000 kilometers. Such collimation is difficult to explain with conventional outgassing models, where material should spread more diffusely as it leaves the nucleus. Loeb and Eric Quito have proposed that the anti-tail might consist of tiny ice particles shed from the sun-facing side of the nucleus. These particles would sublimate before solar radiation could push them back, creating a transient sunward stream. Another paper suggests the anti-tail could be a swarm of objects lagging behind the main nucleus due to non-gravitational acceleration. Other researchers have noted that anti-tails can occur in solar system comets under certain geometric conditions when Earth crosses the comet's orbital plane. But the persistence of 3I-ATLAS's anti-tail across different viewing geometries makes this explanation problematic. The sixth anomaly involves the rotation axis. Recent observations have revealed that the rotation axis of 3I-ATLAS is aligned to within 8 degrees of the sunward direction. This is an unusual orientation that has interesting implications. When a comet's rotation axis points toward the sun, one hemisphere receives continuous sunlight, while the other remains in perpetual darkness. The sunlit side heats up and outgasses, while the dark side stays frozen. This configuration could explain some of the unusual jet activity observed. But here is the puzzle. The alignment between the rotation axis and the sunward direction should only hold at one point in the orbit. As the comet moves around the sun, the solar direction changes, while the rotation axis typically remains fixed in space. Yet 3I-ATLAS appears to maintain this alignment even as its orbital geometry evolves. The probability of the rotation axis randomly aligning so closely with the sun at the distances where 3I-ATLAS was first observed is roughly 0.5%. Loeb has termed this the 14th anomaly and notes that it raises the overall improbability of the object's configuration. The 7th anomaly concerns polarization. Light from 3I-ATLAS shows extreme negative polarization, a pattern unprecedented among all known comets, including Borisov. Polarization describes how light waves oscillate, and the polarization of scattered light depends on the properties of the scattering material. The extreme polarization of 3I-ATLAS suggests its dust particles have unusual shapes, compositions, or size distributions. This might be related to the anti-tail, as unusual particle properties could also explain why material appears to stream toward rather than away from the sun. No satisfactory natural explanation has yet been offered for this anomaly. It remains one of the most puzzling aspects of the object's behavior. The 8th anomaly involves carbon chain depletion. Spectroscopic observations have shown that 3I-ATLAS is depleted in carbon chain molecules like C2 and C3, relative to typical comets. These molecules, formed when carbon-containing ices break down under solar radiation, give many comets their characteristic green glow. Early observations of 3I-ATLAS showed a reddish colour rather than green. This was consistent with the carbon chain depletion. Organics on the surface were outgassing, but the expected green fluorescence was muted. However, post-perihelion images showed the comet turning green, suggesting that C2 was finally being produced as deeper, less processed ices were exposed. The colour change itself became a talking point, though some researchers cautioned against overinterpreting what might be normal cometary evolution. The ninth anomaly concerns water abundance. 3I-ATLAS appears to have an unusually low water abundance relative to carbon dioxide. This ratio, measured by the James Webb Space Telescope and other instruments, differs significantly from typical solar system comets. The elevated CO2 could result from cosmic ray processing over billions of years, as discussed earlier. But the specific ratio observed is toward the extreme end of what models predict even for very ancient objects. Some researchers have questioned whether additional processes might be at work. The 10th anomaly involves the perihelion distance. 3I-ATLAS passed the Sun at a distance of roughly 1.36 astronomical units, just inside the orbit of Mars. This relatively close approach triggered intense outgassing and activity, as expected for any icy body subjected to solar heating. What is unusual is how the perihelion distance relates to the object's overall trajectory. The hyperbolic orbit of 3I-ATLAS was shaped by its incoming velocity and direction. Given those initial conditions, the perihelion distance emerges from orbital mechanics. Loeb has noted that the specific perihelion achieved allows for maximum interaction with the inner solar system, while avoiding the extreme heating that might destroy a more fragile object. Whether this represents fine-tuning or simply the outcome of random orbital parameters remains debated. The 11th anomaly concerns non-gravitational acceleration. As mentioned earlier, 3I-ATLAS displays motion that cannot be explained by gravity alone. Something is pushing the object, altering its trajectory in ways that pure gravitational calculations fail to predict. For most comets, this non-gravitational acceleration is attributed to outgassing. Jets of material erupting from the surface act like tiny rocket engines, nudging the comet off course. The magnitude and direction of this thrust depend on which parts of the surface are active and how much material is being ejected. The non-gravitational acceleration of 3I-ATLAS has been measured and is routinely updated by NASA's Jet Propulsion Laboratory. The values have changed over time as the models have been refined, leading to some controversy about what the true acceleration actually is. What makes this anomaly particularly interesting is its relationship to another remarkable coincidence. The 12th anomaly involves Jupiter's Hill radius. When the trajectory of 3I-ATLAS was projected forward, researchers noticed something extraordinary. The object's closest approach to Jupiter in March 2026 will bring it to approximately 53.4 million kilometers from the giant planet. This distance is almost exactly equal to Jupiter's Hill radius, the sphere of gravitational influence within which objects can potentially orbit the planet. The Hill radius of Jupiter is approximately 53.5 million kilometers. The match is precise to within a fraction of a percent. Loeb has calculated the probability of this coincidence at less than 0.004%, making it one of the most statistically striking anomalies on the list. If 3I-ATLAS were to release small objects or debris as it passes through this region, those objects could potentially enter orbit around Jupiter. They would settle naturally into stable positions near the Hill sphere boundary, where gravitational influences are balanced and orbital maintenance requires minimal energy. Is 3I-ATLAS aiming for Jupiter? Will it deploy something as it passes? These questions sound like science fiction, and most astronomers would dismiss them as unwarranted speculation. But Loeb argues that the coincidence is too precise to ignore entirely. At minimum, it deserves continued observation. The 13th anomaly concerns the object's brightness evolution. 3I-ATLAS brightened as it approached the Sun, as expected. But the rate and pattern of brightening did not perfectly match models derived from solar system comets. There were episodes of rapid brightening that suggested outburst events, followed by periods of relative quiescence. Understanding cometary brightness is notoriously difficult. These objects are dynamic and unpredictable, capable of sudden flares and unexpected fading. The brightness anomalies of 3I-ATLAS may simply reflect this inherent variability. The 14th anomaly, as mentioned earlier, is the alignment of the rotation axis with the sunward direction. And the 15th anomaly is perhaps the most provocative of all. It concerns a potential connection to a mysterious signal detected nearly 50 years ago. But that connection deserves its own exploration. It is a story that spans decades and light years, linking a 72-second radio burst in 1977 to an icy wanderer arriving in 2025. Before we turn to that tale, let us step back and consider what these 15 anomalies collectively suggest. Each anomaly, taken individually, might have a mundane explanation. Statistical flukes happen. Our understanding of comets is incomplete. Interstellar objects are rare, and we may simply be encountering behaviours we have never seen before because we have never had the opportunity to study such objects in detail. But the anomalies compound. The probability of multiple independent improbabilities occurring together is the product of their individual probabilities. If each anomaly has a 1% chance of occurring by chance, and there are 15 independent anomalies, the combined probability drops to essentially zero. Critics of this reasoning point out that the anomalies are not truly independent. Many might share a common cause, such as the object's unusual composition or ancient age. Others might be artifacts of measurement uncertainty rather than real features. The statistical arguments assume a neutral prior, but our priors are not neutral. We expect unusual objects to have unusual properties. The debate continues. As mentioned before, it will be settled not by argument but by evidence. Every new observation of 3I-ATLAS provides data that either supports or challenges the anomaly interpretation. Every new analysis refines our understanding of what is truly unusual versus what merely appears unusual at first glance. What we can say with certainty is that 3I-ATLAS has forced the astronomical community to confront questions it would rather avoid. Are we looking at a natural object with exotic properties or something else entirely? And if something else, what could it possibly be? The answer may lie in the stars, or more precisely in a direction in the sky from which a strange signal once emerged, a signal that has haunted astronomers for almost half a century, the WOW signal connection, a message sent 48 years ago, August 15th, 1977. The Big Ear radio telescope at Ohio State University was scanning the heavens, searching for signals that might indicate intelligent life beyond Earth. The search for extraterrestrial intelligence, or SETI, was still young then, fueled by optimism and the growing realization that the universe contained billions upon billions of stars, many with their own planetary systems. On that summer night, astronomer Jerry Amon was reviewing printouts from the telescope's observations. In those days, data came on paper, long strips marked with numbers and letters representing signal intensity at various frequencies. Most of it was noise, the random crackle of the cosmos. Eamon had learned to scan these printouts quickly, his eye trained to spot anything unusual. Then he saw it. A sequence of characters that stood out from everything around it. 6 EQUJ5. The intensity climbed rapidly from the background level, peaked at an extraordinary value represented by the letter U, then declined back to noise. The entire event lasted 72 seconds. Eamon grabbed a red pen. He circled the sequence and wrote a single word in the margin. Wow! That exclamation would give the signal its name. For nearly 5 decades, the WOW signal has remained the strongest candidate ever detected for an extraterrestrial transmission. It has never been explained. It has never repeated. The signal arrived at a frequency of 1420.4556 MHz, plus or minus 5 kHz. This is significant. The frequency corresponds to the hyperfine transition of hydrogen, the most abundant element in the universe. Hydrogen atoms naturally emit radiation at this frequency, and scientists had long speculated that an intelligent civilization trying to communicate across interstellar distances might choose this channel precisely because it would be universally recognizable. The signal came from the direction of the constellation Sagittarius, near the galactic center. Its duration of 72 seconds matched exactly what the Big Ear would observe if a continuous extraterrestrial beacon were tracked as the Earth's rotation swept the telescope's beam across the sky. Everything about the signal was consistent with an artificial origin beyond our solar system, and yet, despite decades of searching, the signal never returned. Eamon and others pointed the Big Ear back at the same patch of sky repeatedly. Other telescopes joined the hunt. Nothing. Whatever had produced the WOW signal, it had fallen silent, or moved on, or perhaps never existed in the way we imagined. Explanations were proposed: satellite interference, a passing comet releasing hydrogen gas, equipment malfunction, classified military transmissions. none of these theories could be confirmed, and each had significant problems. The WOW signal remained a mystery, filed away in the annals of unexplained phenomena, occasionally revisited but never resolved. Until now. In late September 2025, Avi Loeb published a calculation that sent ripples through the astronomical community. He had traced the trajectory of 3I-ATLAS backward in time, computing where the object would have been on August 15, 1977, nearly 48 years before its discovery. The result was remarkable. On that date, 3I-ATLAS was approximately 600 astronomical units from the Sun, about 600 times the Earth-Sun distance. It was approaching the solar system, from interstellar space, still decades away from its eventual passage through the inner planets, and its position in the sky was startlingly close to the origin point of the WOW signal. Loeb calculated that the arrival direction of 3I-ATLAS coincided with the WOW signal, to within approximately 9 degrees. Given the entire sphere of possible sky directions, the probability of two random events aligning this closely is roughly 0.6%, or about 1 in 167, less than 1%. Not impossible by any means. Coincidences of this magnitude occur regularly in astronomy and elsewhere. But combined with all the other anomalies surrounding 3I-ATLAS, this alignment added another layer to the growing mountain of improbabilities. Could the WOW signal have originated from 3I-ATLAS? The hypothesis sounds fantastical, but Loeb worked through the physics. At 600 astronomical units, a transmitter on 3I-ATLAS would have needed to produce between half a gigawatt and 2 gigawatts of power to generate the detected signal intensity. That is roughly the output of a standard nuclear reactor. If 3I-ATLAS harbored technology, if it was some kind of probe or beacon from another civilization, a 1 gigawatt transmitter would not be implausible. We build such devices ourselves. A civilization capable of launching interstellar probes would certainly be capable of powering them. The frequency choice also made sense in this context. If 3I-ATLAS were approaching our solar system from interstellar space, and if it carried instruments designed to survey planetary systems for signs of life or technology, broadcasting at the hydrogen line would be a logical choice. Any civilization capable of radio astronomy would be listening at that frequency. It is the universal call sign of intelligence, and the duration. 72 seconds corresponds to the time a fixed radio source remains in the Big Ear's beam as Earth rotates. But if the source were moving relative to Earth, the duration could vary. 3I-ATLAS was indeed moving, approaching the solar system at high velocity. The observed duration is at least consistent with the hypothesis, though not uniquely predicted by it. But there are serious problems with this scenario. First, the positional alignment is not perfect. 9 degrees is close on cosmic scales, but it is not exact. The uncertainty in both the WOW signal location and the reconstructed position of 3I-ATLAS 48 years ago is substantial. The apparent alignment might be less significant than it appears. Second, the directional correspondence involves looking backward along 3I-ATLAS's trajectory versus looking at where the signal came from. If 3I-ATLAS emitted the signal, it would have been moving toward us, not sitting stationary in Sagittarius. The geometry is more complex than a simple comparison of sky position suggests. Third, and most critically, the WOW signal was never detected again. If 3I-ATLAS were a broadcasting probe, why did it transmit only once? Why fall silent for 48 years? A beacon designed to attract attention would presumably repeat its signal to increase the chances of detection. One possible answer is that the transmission was not a beacon at all. Perhaps it was a targeted communication, aimed at a specific location that happened to include Earth's position at that moment. Perhaps 3I-ATLAS was reporting back to its makers, and we intercepted a message not intended for us. In that case, the signal would not necessarily repeat in our direction. Another possibility is that the transmission occurred automatically under specific conditions that have not recurred. Perhaps 3I-ATLAS broadcasts only when passing through certain regions of space, or when detecting specific signatures from a stellar system. Whatever triggered the 1977 signal might not have triggered again until now, when the object is deep within our solar system. Or perhaps the connection is entirely coincidental. Perhaps the WOW signal had nothing to do with 3I-ATLAS, and we're drawing patterns where none exist. The mainstream astronomical community strongly favours this last interpretation. Most researchers consider the WOW signal lobe connection to be speculative at best and misleading at worst. They point out that low-probability coincidences are inevitable when you look for them, that the statistical arguments rest on assumptions that may not be valid, and that there is no direct evidence linking the two phenomena. But there was a development in October 2025 that gave the connection new life. On October 24th, the Meerkat radio telescope at the South African Radio Astronomy Observatory achieved something that had previously eluded researchers. They detected a radio signal from 3I-ATLAS. Now, before we get too excited, let us be clear about what was actually detected. The signal was not a coded transmission. It was not evidence of artificial broadcasting. What Meerkat observed was an OH absorption line, a natural signature of hydroxyl molecules that form when water breaks down under ultraviolet radiation. This detection was important for conventional comet science. It confirmed that 3I-ATLAS was actively outgassing, producing water vapor that was being dissociated by solar ultraviolet light. The hydroxyl signal allowed researchers to study the comet's activity in the radio band, complementing observations at other wavelengths. But for those who had hoped 3I-ATLAS might reveal itself through radio transmission, the detection was both tantalizing and frustrating. The comet had finally been observed with radio telescopes, but the signal was natural, not artificial. No encoded messages, no deliberate broadcasts, just the normal chemistry of an icy body warming in the sun. Still, the detection prompted renewed interest in the WOW signal hypothesis. Abel Mendez, a researcher at the Planetary Habitability Laboratory at the University of Puerto Rico at Arecibo, announced plans to analyze newly derived properties of the WOW signal in an upcoming paper. The goal is to create the clearest picture yet of what the signal was and where it came from, potentially testing whether a connection to 3I-ATLAS is plausible. Meanwhile, Loeb continues to advocate for radio observations of 3I-ATLAS at frequencies around the hydrogen line. If the object were to emit even a faint signal at 1420 MHz, it would revive the WOW signal hypothesis dramatically. So far, no such emission has been detected. Let us consider what it would mean if the connection were real. If 3I-ATLAS transmitted the WOW signal in 1977, then this object is not merely an interstellar comet. It is an artifact of extraterrestrial intelligence, a probe or beacon that has been operating for at least 48 years and possibly much longer. Its journey through our solar system would not be a random occurrence, but a deliberate visitation. The implications would be staggering. We would have confirmation that we are not alone in the universe, that other intelligences exist and have the capability to send objects across interstellar distances. The questions would multiply endlessly. Who sent it? From where? What does it want? Is it merely observing, or does it have other purposes? Are there more like it? These are profound questions, the kind that would reshape human civilization's understanding of its place in the cosmos, and they rest on what is currently a slender thread of evidence, a 9-degree alignment and a 1% probability. Science demands caution. Extraordinary claims require extraordinary evidence, and we do not yet have anything close to that standard. The WOW signal remains unexplained, and 3I-ATLAS remains anomalous, but the link between them is speculative. Yet there is value in exploring the speculation. By seriously considering the possibility that 3I-ATLAS and the WOW signal are connected, we sharpen our understanding of what evidence would confirm or refute such a hypothesis. We identify what observations to prioritize. We remain open to possibilities that a purely conventional mindset might dismiss prematurely. The WOW signal lasted 72 seconds and then vanished into silence. 3I-ATLAS will pass through our solar system over a period of months and then vanish into the darkness between stars. Both phenomena are transient, unrepeatable, windows that open briefly and then close forever. If they are connected, we have a unique opportunity to study the source of a decades-old mystery. If they are not, we lose nothing by having looked. Either way, the coincidence haunts us. A signal from 1977, a comet in 2025, two unexplained phenomena, separated by half a century of time and billions of kilometers of space, yet arriving from the same direction in the sky. The universe is vast and strange. Sometimes coincidences are just coincidences, and sometimes they are not. As 3I-ATLAS continues its journey outward, taking its secrets with it, the WOW signal remains on the books, unexplained, waiting for the day when someone finally cracks its code. Perhaps that day will never come. Perhaps the answer has been sailing through our solar system all along, close enough to study but too far to reach. We may never know for certain, but we can keep watching, we can keep listening, and we can keep asking the questions that drive science forward, even when the answers seem impossibly far away. Close Encounters, Mars, Venus, and the spacecraft that watched. On October the 3rd, 2025, something remarkable happened in the skies above Mars. An object from another star system passed within 29 million kilometers of the red planet, closer than any other planetary encounter during its journey through the inner solar system. At that distance, 3I-ATLAS was roughly 1/5 the average separation between Earth and Mars. It was close enough that Mars-based observatories could capture detailed images, close enough that the encounter would slightly alter the object's trajectory through gravitational deflection, close enough that if anything were to happen, if the comet were to fragment or maneuver, or do anything unexpected, robotic eyes would be watching, and they were. In the weeks surrounding the Mars flyby, an unprecedented coordination of spacecraft turned their instruments toward the interstellar visitor. The European Space Agency operates 2 Mars orbiters, the veteran Mars Express, and the newer ExoMars Trace Gas Orbiter, often called TGO. Both spacecraft received commands to observe 3I-ATLAS during its closest approach. TGO was equipped with the CASSES instrument, a high-resolution camera designed to study surface features on Mars. But cameras can be pointed anywhere, and CASSES was directed toward the approaching comet. The images it captured were the closest ever obtained of an interstellar object. What did they show? A fuzzy blob. Yes, because 3I-ATLAS remained millions of kilometers distant even at its closest, but a fuzzy blob with structure. The coma surrounding the nucleus was clearly visible, along with hints of the jets and tails that other telescopes had been tracking. For the first time, we had views of an interstellar comet from an interplanetary vantage point. Mars Express also observed the comet using its high-resolution stereo camera, though with less success than TGO. The exposure times may not have been optimized, and the comet proved difficult to detect against the background. Still, the attempt contributed to the global effort to characterize 3I-ATLAS from every available platform. NASA's Mars Reconnaissance Orbiter joined the campaign with its HiRISE instrument, arguably the most powerful camera ever sent to another planet. On October 2nd, MRO captured images of 3I-ATLAS from approximately 19 million miles away. The resulting photograph showed the comet as a bright smear against the darkness, with enough detail to help refine calculations of its trajectory. The significance of the MRO observation went beyond mere imagery. The precise position data extracted from these images allowed researchers to constrain the comet's path through space with unprecedented accuracy. The orbital calculations that predict where 3I-ATLAS will go next depend critically on such observations. Every additional data point reduces uncertainty and sharpens our forecasts. But there was a complication. NASA was experiencing significant disruptions during this period, and some data from Mars missions was not immediately released to the public. The delay frustrated researchers and the public alike, leading to speculation that perhaps something was being withheld. In reality, the explanation appears mundane. Bureaucratic and technical challenges slowed the release of data, but the observations were eventually shared and incorporated into the scientific record. Conspiracy theories about NASA hiding information about 3I-ATLAS found no support in the facts. The Chinese National Space Administration also contributed observations. Tianwen-1, China's Mars orbiter, turned its instruments toward 3I-ATLAS and successfully captured images. The international cooperation with space agencies from Europe, America and China, all observing the same target, demonstrated the global scientific interest in this interstellar visitor. Perhaps most poignant was the participation of NASA's Perseverance rover, sitting on the Martian surface. From its position in Jezero crater, Perseverance had a unique perspective on the comet. Using its Mastcam-Z imaging system, the rover attempted to photograph 3I-ATLAS in the Martian sky. The images were challenging to obtain. Mars has a thin atmosphere, but it does scatter some light, creating a glow that can obscure faint objects. The comet was dim, moving against a backdrop of stars, but Perseverance succeeded, adding its views to the growing catalogue of 3I-ATLAS observations. Think about that for a moment. A robot sitting on the surface of another planet, a machine we built and launched and landed on Mars, looked up at the sky and photographed a visitor from another star. If that does not stir something in you, nothing will. The Mars encounter was critical for refining our understanding of 3I-ATLAS's trajectory. When an object passes close to a massive body like a planet, its path bends due to gravity. The amount of deflection depends on the geometry of the encounter and the masses involved. By measuring exactly how much 3I-ATLAS curved around Mars, scientists could better determine the object's mass and confirm that its motion was influenced by factors beyond gravity alone. This is where the non-gravitational acceleration comes back into focus. The trajectory calculations performed before the Mars encounter assumed a certain level of outgassing thrust. The actual observations allowed researchers to check those assumptions against reality. The results showed that 3I-ATLAS was indeed experiencing non-gravitational acceleration, but the precise magnitude was difficult to pin down. The models required adjustments, and different assumptions about how the acceleration varied with distance from the Sun led to different predictions for the object's future path. One particularly controversial finding emerged from these calculations. When the new trajectory was projected forward to the March 2026 Jupiter encounter, the predicted closest approach distance matched Jupiter's hill radius almost exactly. As mentioned in our discussion of anomalies, this coincidence has probabilities measured in fractions of a percent. But we should be careful about overinterpreting such coincidences. The trajectory of 3I-ATLAS depends sensitively on parameters that are still uncertain. Small changes in the assumed non-gravitational acceleration can shift the predicted Jupiter encounter distance by millions of kilometers. The apparent match with the hill radius might be a statistical artifact that disappears as observations improve. Beyond Mars, other spacecraft contributed to the 3I-ATLAS observation campaign. NASA's MAVEN mission, designed to study the Martian atmosphere, used its ultraviolet instrument to observe the comet. MAVEN detected hydrogen atoms surrounding 3I-ATLAS, evidence of water molecules breaking apart under solar radiation. This complemented the hydroxyl detection by MeerKAT and confirmed that water ice was a significant component of the comet's composition. Moving outward from Mars, we encountered another coincidence. The Psyche spacecraft, en route to the metal asteroid of the same name, passed relatively close to 3I-ATLAS in early September 2025. Astrophysicist Marshall Eubanks calculated that Psyche came within about 45 million kilometers of the comet. Psyche was not designed to observe comets, and its instruments are optimized for studying metallic asteroid surfaces. But the spacecraft carried cameras, and there was hope that it might capture useful images of the interstellar visitor during its serendipitous approach. The Jupiter Icy Moons Explorer, or JUICE, also entered the picture. This European Space Agency mission, launched in 2023 and currently en route to Jupiter, found itself in a favourable position to observe 3I-ATLAS. Between November 2nd and 25th of 2025, JUICE trained its instruments on the comet. The timing was fortunate. This observation window captured 3I-ATLAS shortly after perihelion, when the comet was at its most active. Solar heating had driven intense outgassing, and the coma and tails were well developed. JUICE's cameras and spectrometers gathered data that complemented ground-based and Mars-based observations. The images from JUICE showed the coma extending around the nucleus, with hints of the multiple tails that amateur astronomers had been photographing from Earth. The spacecraft's unique vantage point, approaching from a different angle than Earth-based telescopes, revealed structures that might otherwise have been hidden or ambiguous. Even NASA's Lucy mission contributed observations. Lucy, sent to study the Trojan asteroids that share Jupiter's orbit, spotted 3I-ATLAS from approximately 240 million miles away. The comet appeared as a faint smudge in Lucy's images, but every data point helped refine the global understanding of the object's behavior and trajectory. Solar observing missions also played a role. As 3I-ATLAS approached perihelion in late October, it entered the field of view of instruments designed to monitor the Sun. NASA's STEREO mission, which studies solar activity from 2 spacecraft orbiting the Sun, captured images of the comet passing through the inner solar system. The PUNCH mission, launched to study the solar wind, observed 3I-ATLAS from September 28th to October 10th. The images showed the comet's tail as a short elongation, revealing how solar wind and radiation pressure were shaping the material streaming from the nucleus. Perhaps most dramatic was the observation by the ESA-NASA Solar and Heliospheric Observatory, known as SOHO. This spacecraft, positioned at the L1 Lagrange point between Earth and the Sun, was expected to observe 3I-ATLAS as it passed through its field of view around perihelion. Initially, scientists thought the comet might be too faint for SOHO to detect, but careful image processing and stacking of multiple observations revealed the comet in SOHO's coronagraph images. 3I-ATLAS appeared as a faint streak against the solar corona, a visitor from another star briefly silhouetted against our own. The coordination of all these observations represents one of the most intensive campaigns ever mounted to study a single small body. Ground-based telescopes, space telescopes, Mars orbiters, Mars rovers, interplanetary probes, and solar observatories all contributed data. The scientific community mobilized resources across continents and across the solar system to capture every possible photon from this once-in-a-lifetime visitor. And then there was Europa Clipper, whose observations were released just yesterday, revealing details about 3I-ATLAS's composition and outgassing that could only be obtained from its unique sunward vantage point. What have we learned from all these observations? First, 3I-ATLAS is unquestionably a comet. It has a nucleus, a coma, and tails. It outgasses water, carbon dioxide, carbon monoxide, and other volatiles. It brightens as it approaches the Sun and fades as it recedes. By every conventional measure, it behaves like a comet should. Second, it is an unusual comet. The anomalies discussed earlier, the anti-tail, the polarization, the chemical abundances, the trajectory coincidences, these are real features supported by multiple independent observations. Something about 3I-ATLAS is different from typical solar system comets, even if we do not yet fully understand what. Third, the object passed through the inner solar system without incident. It did not fragment. It did not maneuver unexpectedly. It did not emit signals or deploy devices. Whatever 3I-ATLAS is, it behaved during its planetary encounters exactly as a natural body would be expected to behave. This last point is significant for those who entertain exotic hypotheses. If 3I-ATLAS were an alien probe, the Mars encounter would have been an obvious opportunity for it to take action. Mars is the most promising target for extraterrestrial interest in our solar system, a world that may have harbored life in the past and could potentially support human colonization in the future. A probe interested in our planetary system would logically focus attention on Mars, but nothing unusual happened. 3I-ATLAS swept past the red planet photographed by our robots, tracked by our telescopes, and continued on its way without any behavior that could not be explained by cometary physics. Does this prove the object is natural? Not definitively. An advanced probe might be programmed for passive observation only, collecting data without taking detectable action. It might be dormant, waiting for conditions or triggers we cannot anticipate. It might simply not care about Mars the way we assume an extraterrestrial intelligence would. But the simplest explanation remains the likeliest. 3I-ATLAS is an interstellar comet, an ancient wanderer from another star, passing through our system by chance. Its anomalies likely have natural explanations we have not yet identified. Its trajectory coincidences are probably statistical flukes amplified by human pattern seeking. Probably. Likely. These hedging words persist because certainty remains elusive. The observations continue to accumulate, and with each new data point, our picture of 3I-ATLAS comes into sharper focus. What happens next will further test our understanding. Jupiter awaits in March 2026, and between now and then, ground-based telescopes will continue monitoring the comet as it fades slowly into the outer darkness. For now, the spacecraft have done their part. Mars orbiters, solar observers, interplanetary probes, all have contributed their pixels and photons to the collective portrait of an interstellar visitor. When the history of 3I-ATLAS is written, This chapter will describe how humanity marshalled its robotic eyes across the solar system to study a traveller from another star. We may not have all the answers, but we asked the questions, we looked, and in science, that is always the first step. The colour that should not change. Red to green to gold. There is something almost magical about watching a comet change colour. It speaks to the dynamic nature of these objects, to the violent chemistry occurring on their surfaces as ancient ices meet modern sunlight. When 3I-ATLAS began shifting its appearance from red to green and then to gold, astronomers took notice. These chromatic transformations were telling us something important about the composition and evolution of our interstellar visitor. Let us start with the red. When 3I-ATLAS was first observed in detail, its coma displayed a distinctly reddish tint. Images from the Gemini South Telescope in Chile, posted in early September 2025, showed this colour clearly. The glow surrounding the nucleus was not the characteristic green of many solar system comets, but rather a warmer, more organic hue. Redness in comets typically indicates the presence of tholins, complex organic molecules formed when simple ices and gases are irradiated over long periods. These compounds are common on outer solar system bodies like Titan and Pluto, where billions of years of cosmic ray bombardment have transformed surface materials into dark, reddish organic gunk. For 3I-ATLAS, the red colour made sense. If the object truly was 7 to 14 billion years old, it would have accumulated an enormous dose of cosmic radiation during its journey through interstellar space. The surface layers would be thoroughly processed, rich in the irradiated organics that produce reddish coloration. The red also explained something puzzling about the early spectroscopic observations. 3I-ATLAS appeared to be depleted in carbon chain molecules like C2, the diatomic carbon that gives most comets their green glow. If the surface was dominated by ancient processed material, the fresh ices containing carbon chain precursors might be buried beneath an organic crust. But comets are not static objects. They evolve as they approach the sun, shedding their outer layers and exposing fresh material from below. As 3I-ATLAS dove toward perihelion, solar heating intensified. The processed crust began to sublimate, revealing whatever lay beneath, and what lay beneath was different. In early September, amateur astrophotographers Michael Yeager and Gerald Riemann captured images of 3I-ATLAS during a total lunar eclipse from their observing site in Namibia. To their surprise, the comet appeared green with a bluish tinge. The gas-rich coma was clearly visible in both blue and green filters. The transformation was striking. The reddish object of summer had begun to show the emerald glow characteristic of active comets. Green in comets comes primarily from diatomic carbon, C2, molecules that absorb ultraviolet sunlight and re-emit the energy as visible green light. This process, called fluorescence, is well understood. When solar radiation breaks down carbon containing ices, free carbon atoms combine briefly to form C2 before being further dissociated. During their brief existence, these molecules glow green. But here was the puzzle. Earlier spectroscopic observations had suggested that 3I-ATLAS was unusually depleted in carbon chains. Where was the C2 coming from? One possibility is that the depletion was only skin deep. The ancient irradiated surface might have been stripped of C2 precursors, but fresh ice beneath still contained the necessary ingredients. As the sun heated the comet and drove off the processed crust, unaltered material emerged and began producing the expected green fluorescence. Another possibility involves the complex layering that might exist within an interstellar comet. If 3I-ATLAS formed in one environment, spent time in another, and then drifted through interstellar space for billions of years, its internal structure could be heterogeneous. Different regions might have different compositions, revealed sequentially as thermal erosion works its way inward. The green became more pronounced after perihelion. Images from the Gemini North Telescope in late November showed the comet glowing distinctly green, much more so than it had appeared months earlier. The National Science Foundation's NOIR lab, which operates the Gemini telescopes, confirmed that the green was consistent with diatomic carbon emission. By this point, 3I-ATLAS had swung around the sun and was heading back out toward the outer solar system. The perihelion passage had been intense. Solar radiation had baked the sun facing side of the nucleus, driving off enormous quantities of volatile material. The The coma had expanded, the tails had stretched, and the colour had shifted definitively from the red of ancient organics to the green of active outgassing. Then came another change. In mid-December, just days before the closest approach to Earth, observers noted that 3I-ATLAS appeared to be shifting again. Reports emerged describing a golden or yellowish tint to the coma. The Daily Star reported on December 16th that the comet's colour had changed from red to green and then to gold. What could cause a golden colour? The answer likely involves the specific mix of materials being released at this stage of the comet's evolution. As a comet recedes from the Sun, its activity does not shut off instantly. The nucleus retains heat absorbed during perihelion, and this thermal energy continues driving sublimation even as solar input decreases. But the composition of the outgassing may change. Different ices have different sublimation temperatures, and as the comet cools, the relative contributions of various species shift. Water ice, carbon dioxide ice, and carbon monoxide ice all sublimate at different temperatures. Early in the outbound journey, when the nucleus is still warm, the more volatile species dominate. As cooling progresses, the contribution of a water increases relative to the more volatile ices. These compositional changes affect the colour of the coma. Different molecules scatter and emit light differently. A coma rich in dust and certain gas species might appear golden or yellowish, especially when viewed through specific filter combinations. There is another interpretation, though, one that carries more sobering implications. Some researchers have suggested that the colour changes in 3I-ATLAS might indicate that the object is running out of ice. The transition from red to green to gold could represent successive layers of material being stripped away, with each layer having a different composition due to billions of years of interstellar processing. If this interpretation is correct, 3I-ATLAS might be transitioning from an active comet to a dormant post-cometary asteroid. The volatile ices that drive cometary activity would be largely exhausted, leaving behind a rocky, dusty nucleus incapable of producing significant outgassing. This is a natural process that occurs with solar system comets. Over repeated perihelion passages, a comet's ices are gradually depleted. Eventually, the object becomes dormant, indistinguishable from an asteroid. Many near-Earth asteroids may be dead comets that have exhausted their volatile supply. For 3I-ATLAS, with its enormous time spent in interstellar space, the ice budget might be particularly constrained. Even before entering our solar system, cosmic ray processing would have converted some ices to less volatile forms. The perihelion passage in 2025 delivered a significant thermal shock. The combination might have pushed the object close to the end of its active life. This is speculative, of course. We do not know how much ice remains locked within 3I-ATLAS. The nucleus could contain vast reserves that will sustain activity for many more passages around stars if it ever encounters another star. Or it could be on its last legs, sputtering out the final remnants of volatiles accumulated in another solar system billions of years ago. The colour changes also sparked debate about whether any changes were occurring at all. Some scientists cautioned against overinterpreting apparent colour variations. Bryce Bolin and colleagues, whose team has extensively studied 3I-ATLAS, stated that they did not have evidence for the gas coma changing colours. Different filters, different observing conditions, and different image processing techniques can all affect apparent colour. What looks like a physical change might be an artefact of how the data was collected and analysed. This is an important caveat. Cometary observations are notoriously difficult to interpret. These objects are faint, diffuse, and embedded in backgrounds of scattered light and cosmic rays. Extracting reliable colour information requires careful calibration and standardisation that is not always achieved, especially in images shared informally on social media. The mainstream scientific view is that the apparent colour evolution of 3I-ATLAS is real in broad strokes, even if specific details are uncertain. The object did appear redder early in its journey and greener after perihelion. Whether it is now turning gold remains to be confirmed by rigorous analysis of calibrated data. Regardless of the exact colours, the underlying story is clear. 3I-ATLAS is a dynamic object undergoing rapid change as it interacts with our Sun. The surface that greeted us in July is not the same surface we see in December. Layers have been stripped away, hidden ices have been exposed. The billion-year crust of interstellar processing is being peeled back, revealing whatever primordial material lies beneath. In that sense, 3I-ATLAS is performing an unintentional geology experiment. It is coring itself for us, drilling down through its own history with each pulse of outgassing. The red was the ancient surface, the green was the fresher ice below. The gold, if real, might be something else entirely, perhaps the final layers before the rocky nucleus itself. We will not be able to watch this experiment to its conclusion. 3I-ATLAS is receding from the sun and will continue to cool. Activity will decline. The coma will fade. Eventually the object will be too dim to observe, even with our most powerful telescopes. But for a few months, we had a front-row seat to the transformation of an interstellar visitor. We watched as solar heat stripped away billions of years of accumulated history, layer by layer, colour by colour. It was geology at cosmic scales, chemistry in action, a reminder that even ancient objects are not static, that the universe is always changing, always revealing, always offering new mysteries to those who watch carefully enough. The red was the past, the green was the present. The gold might be the future, a future in which 3I-ATLAS falls silent, its fire spent, its ices exhausted, drifting forever as a quiet husk through the endless dark. Or perhaps not. Perhaps beneath the gold lies more ice, more colour, more surprises. We will not know unless we keep watching. And as long as the comet remains visible, that is exactly what we intend to do. X-ray eyes on. An interstellar ghost. What the telescopes revealed. When you look at a comet through a backyard telescope, you see reflected sunlight and glowing gas. The image is beautiful but limited, showing only what visible light can reveal. To truly understand what a comet is made of, how it interacts with its environment, and what processes are occurring in its extended atmosphere, you need to look beyond the visible spectrum. X-rays offer a window into a completely different aspect of cometary physics. They reveal violent interactions, high energy collisions, the places where the solar wind meets cometary gas in an invisible war of particles and fields. And in late 2025, two of the world's most powerful X-ray observatories turned their gaze toward 3I-ATLAS, capturing the first X-ray images ever obtained of an interstellar comet. The first detection came from Japan's X-RISM Observatory, a joint mission with NASA and the European Space Agency. X-RISM, which stands for X-ray Imaging and Spectroscopy Mission, launched in September 2023 and carries some of the most sensitive X-ray instruments ever flown. Between November 26th and 28th of 2025, X-RISM conducted a target of opportunity observation of 3I-ATLAS. The spacecraft's X-TEND instrument, a soft X-ray imager, stared at the comet for approximately 17 hours, accumulating enough photons to construct an image. What it captured was extraordinary. The X-ray data revealed a diffuse halo of emission extending roughly 400,000 kilometers from the nucleus of 3I-ATLAS. That distance is about the same as the separation between Earth and the Moon. An invisible sphere of X-ray light, nearly as wide as the orbit of our natural satellite, was glowing around the interstellar visitor. This was not light emitted by the comet itself. Comets are far too cold to produce X-rays thermally. Even at perihelion, the surface temperature of 3I-ATLAS would have been measured in hundreds of degrees Kelvin at most, not the millions of degrees needed for direct X-ray emission. Instead, the glow resulted from a process called charge exchange. To understand charge exchange, you need to think about what happens when the solar wind encounters a comet. The solar wind is a continuous stream of charged particles, mostly protons and electrons, flowing outward from the sun at hundreds of kilometers per second. Mixed in with these are heavier ions, atoms of elements like oxygen, carbon and nitrogen, that have been stripped of most or all of their electrons by the intense heat of the solar corona. These highly charged ions are hungry for electrons. When they encounter neutral gas molecules released by a comet, they grab electrons to fill their empty shells. The capture process is violent on atomic scales. The incoming ion snatches an electron from a gas molecule, leaving both particles in excited states. As the newly captured electron settles into its orbital, it releases energy in the form of X-ray photons. This charge exchange process has been observed in dozens of solar system comets since the phenomenon was first discovered in the late 1990s. It creates a characteristic soft X-ray glow wherever the solar wind interacts with the neutral gas of a cometary coma. The brightness and spatial extent of the glow depend on how much gas the comet is releasing and how dense the solar wind is at that location. For 3I-ATLAS, the XR-ism observation confirmed that the comet was actively outgassing at significant rates. The extended X-ray halo indicated that neutral gas molecules, primarily water vapor, and its dissociation products, were streaming outward from the nucleus and interacting with the solar wind across a vast volume of space. But XRISM provided more than just an image. The observatory's Resolve instrument is capable of high-resolution X-ray spectroscopy, separating the incoming X-rays by wavelength to reveal which ions are producing the emission. The spectral data from 3I-ATLAS showed signatures of carbon, nitrogen, and oxygen ions, exactly what would be expected from charge exchange between the solar wind and common cometary gases. Approximately a week after the XRISM observation, the European Space Agency's XMM Newton Observatory took its turn. XMM Newton, launched in 1999, is one of the most powerful X-ray telescopes ever built. Its European photon imaging camera, known as EPIC, can detect X-rays with exceptional sensitivity across a wide field of view. On December 3, 2025, XMM Newton devoted approximately 20 hours to observing 3I-ATLAS. The resulting image is hauntingly beautiful. Against a dark background representing the near absence of X-rays, a bright red spot marks the nucleus of the comet. Surrounding this central beacon, gradients of purple and blue indicate decreasing X-ray intensity as one moves outward from the core. The emission extends well beyond the immediate vicinity of the nucleus, tracing the boundary between cometary gas and the solar wind. The XMM Newton observation occurred when 3I-ATLAS was approximately 175 to 177 million miles from the spacecraft, at a heliocentric distance of about 1.9 astronomical units. The comet had passed perihelion roughly 5 weeks earlier and was beginning its long journey back toward interstellar space. Despite the increasing distance from the Sun, 3I-ATLAS remained X-ray bright. The outgassing had not yet subsided significantly, and the charge exchange process continued to operate wherever the solar wind met the comet's expanding coma. Comparing the two X-ray observations, separated by about a week, allowed researchers to track the evolution of the charge exchange region. As the comet moved outward, and its activity presumably began to decline, the X-ray signature should fade correspondingly. The XRISM and XMM Newton data, combined with continuing ground-based observations, would reveal how rapidly this decline was occurring. The X-ray detections of 3I-ATLAS are scientifically significant for several reasons. First, they confirm that the same physical processes observed in solar system comets also operate in interstellar comets. This might seem obvious, but it was not guaranteed. 3I-ATLAS formed around another star, under potentially very different conditions. Its composition might have been exotic enough to produce unexpected behavior when interacting with the solar wind. The fact that the X-ray emission looks similar to that of solar system comets suggests that, at least in this respect, 3I-ATLAS is not fundamentally different from the icy bodies in our own cosmic backyard. Second, the X-ray data provide information about gas species that are difficult to detect at other wavelengths. Optical and infrared telescopes are excellent at detecting certain molecules like water, carbon dioxide, and various organic compounds. But they struggle with some of the simpler, lighter species like molecular hydrogen and nitrogen. X-ray observations, through the charge exchange process, are sensitive to these light elements because they involve the capture of electrons by solar wind ions, and the solar wind carries ions of many different elements. ESA noted that X-ray data are particularly sensitive to diatomic hydrogen and nitrogen, making X-ray observations a powerful tool for probing aspects of cometary composition that would otherwise remain hidden. Third, the X-ray observations provide constraints on the gas production rate of 3I-ATLAS. The brightness of the charge exchange emission depends on how much neutral gas is available to interact with the solar wind. By modelling the X-ray intensity and comparing it to the known properties of the solar wind, researchers can estimate how rapidly the comet is releasing material. Preliminary analyses suggest that 3I-ATLAS was outgassing vigorously at the time of the X-ray observations, consistent with the bright coma and extended tails visible at optical wavelengths. The comet's activity rivaled that of moderately active solar system comets, despite its alien origin and ancient age. Fourth, and perhaps most intriguingly, the X-ray observations offer a unique perspective on the geometry of the comet's gas distribution. The charge exchange emission is brightest, where the solar wind is densest, and where the cometary gas is most concentrated. By mapping the X-ray emission across the coma, researchers can trace the three-dimensional structure of the gas outflow. This is where the anti-tail mystery intersects with the X-ray data. If there truly is material streaming toward the Sun rather than away from it, that material should also participate in charge exchange. The X-ray observations might reveal whether the anti-tail is composed of neutral gas, which would glow in X-rays, or purely dust, which would not. The analyses are ongoing. X-ray data requires careful processing to separate the genuine cometary signal from instrumental backgrounds and cosmic X-ray sources. The extended emission from 3I-ATLAS is faint compared to the readout noise and scattered X-rays that contaminate any space-based observation. Extracting reliable information demands sophisticated statistical techniques and careful calibration. But the preliminary results are clear. 3I-ATLAS glows in X-rays, just as solar system comets do. The glow extends hundreds of thousands of kilometers from the nucleus. The spectral signatures indicate charge exchange between the solar wind and standard cometary gases. In the X-ray band, at least, the interstellar visitor looks remarkably familiar. There is a philosophical dimension to these observations worth pondering. X-rays are invisible to human eyes. We cannot look at 3I-ATLAS and see its X-ray halo, no matter how powerful our telescopes or how dark our skies. This aspect of the comet's existence is accessible only through technology, through instruments we have built and launched into orbit around Earth. In a sense, the X-ray emission from 3I-ATLAS has been occurring for months, ever since the comet entered the solar wind. But until Grissom and XMM Newton looked, that emission existed without being observed, a tree falling in a cosmic forest with no one to hear. Now we have heard. We have seen the invisible glow of an interstellar ghost, a halo of high-energy light produced by the violent marriage of alien gas and solar particles. That glow tells us that 3I-ATLAS is made of ordinary stuff, ice and rock and dust, releasing water and carbon compounds just as our own comets do. It tells us that the physics of the solar wind is the physics of all stellar winds, that charge exchange occurs around alien suns just as it occurs around ours. It tells us that the universe operates by consistent rules, that a comet from billions of years ago and billions of kilometers away still obeys the same equations that govern the ice balls in our own Oort cloud. And it tells us that some mysteries transcend the exotic. We hoped, perhaps, that X-ray observations would reveal something strange about 3I-ATLAS, some anomaly that would set it apart from ordinary comets. Instead, the X-ray data show a comet behaving like a comet, ancient, interstellar, covered in anomalies at other wavelengths, but ultimately still just an icy body warming in the light of an unfamiliar star. The X-ray glow will fade as 3I-ATLAS recedes. The charge exchange will diminish as outgassing declines, and the comet moves into the outer solar system, where the solar wind is weaker. Eventually, the invisible halo will disappear entirely, and 3I-ATLAS will drift onward as a dark, cold wanderer once more. But for a few months, in late 2025, we saw what our eyes could never show us. We glimpsed the violence hidden within the beauty, the atomic collisions that accompany every cometary passage, the physics that connects our sun to every star that has ever shone. X-ray eyes on an interstellar ghost, and what they found was strangely, wonderfully ordinary. The anti-tail mystery and the jets, pointing toward the sun. There is something deeply wrong about a comet that points toward the sun. Everything we know about cometary physics tells us that tails should stream away from our star, pushed by the relentless pressure of solar radiation and the supersonic wind of charged particles flowing outward from the corona. Dust grains and gas molecules released from a comet's nucleus should accelerate away from the sun, creating the classic tail that has inspired wonder and terror throughout human history. Yet from the very first detailed images, 3I-ATLAS has displayed a prominent feature pointing in precisely the wrong direction. A jet of material, tightly collimated and persistently sunward, defying the conventional understanding of how comets should behave. The anti-tail was visible in the earliest Hubble Space Telescope observations, captured on July 21, 2025, when 3I-ATLAS was still approaching the Sun from beyond the orbit of Mars. At that point, the object was nearly 3 astronomical units from Earth, and the anti-tail was already apparent, a spike of brightness extending toward the solar direction. This early appearance was itself unusual. Anti-tails in solar system comets are typically transient phenomena, appearing briefly when Earth crosses the comet's orbital plane, and our line of sight happens to align with dust particles trailing behind the nucleus. These geometric anti-tails are perspective effects rather than physical structures, appearing and disappearing as the viewing geometry changes. But the anti-tail of 3I-ATLAS did not appear and disappear. It persisted through changing orbital geometries, visible in observation after observation across multiple months. It was still present in Hubble images taken on November the 30th, when the comet was receding from the Sun at a distance of nearly 2 astronomical units from Earth. Whatever was causing this feature, it was not a simple perspective effect. The collimation of the anti-tail added to the puzzle. In ground-based images from amateur and professional astronomers alike, the sunward jet appeared remarkably narrow, maintaining a tight beam out to distances of hundreds of thousands of kilometers from the nucleus. Gas and dust released from a comet typically spread diffusely as they move away from the source. The tight collimation of the anti-tail suggested some focusing mechanism or an unusual particle population that resisted spreading. Avi Loeb devoted considerable attention to this mystery. In papers co-authored with Eric Quito, he proposed that the anti-tail might consist of tiny ice particles shed from the Sun facing side of 3I-ATLAS. These particles would be ejected toward the Sun by the outgassing process itself, propelled by the asymmetric sublimation of surface ices. Here is how the model works. When sunlight strikes the Sun facing side of a comet, it heats the surface and causes ices to sublimate directly into gas. This gas expands rapidly, carrying dust and small particles with it. The expansion occurs preferentially in the direction perpendicular to the surface, which on the Sun, facing side means toward the Sun. Small particles lifted from the surface would initially move toward the Sun, propelled by the outflowing gas, but solar radiation pressure would then begin pushing them back. For most particles, this radiation pressure would quickly reverse their motion and sweep them into the conventional dust tail. But very small ice particles might behave differently. Ice is highly reflective and partially transparent to solar radiation. Depending on the particle size and composition, the radiation pressure on ice grains could be significantly reduced compared to rocky dust. These ice particles would continue moving sunward for a longer period before being turned around. Furthermore, ice particles sublimate. As they move toward the Sun and warm up, they shrink and eventually disappear entirely. A population of tiny ice grains could create a transient sunward stream that vanishes before radiation pressure can push it back. The anti-tail would then consist of continuously replenished ice particles, a steady-state feature sustained by ongoing ejection and sublimation. This model is plausible but difficult to confirm observationally. We cannot directly image individual ice particles at the distances involved. The best we can do is observe the collective scattering of sunlight from the particle population and compare it to model predictions. Another explanation for the anti-tail involves the non-gravitational acceleration of 3I-ATLAS. If the comet is experiencing a push away from the Sun, as the JPL Horizons data suggests, then objects that separate from the main nucleus might fall behind rather than streaming ahead. A swarm of fragments or debris ejected during outbursts could accumulate in the sunward direction, simply because the main body is accelerating away from them. This interpretation connects the anti-tail to the broader mystery of the comet's anomalous motion. The same force that pushes 3I-ATLAS away from the Sun would cause ejected material to lag behind, creating an apparent sunward tail. In December 2025, new observations added another dimension to the mystery. A paper reporting periodic wobbles in the anti-tail jet suggested that the feature is connected to the rotation of the nucleus. The study, analysing images from July and August, found that the position angle of the anti-tail oscillated with a period of approximately 7.74 hours, plus or minus about 20 minutes. This periodicity implies that the jet source is not centered on the rotation axis but offset by some angle. As the nucleus rotates, the jet precesses around a cone, causing the observed position angle to wobble. The amplitude of the wobble was small, only about 8 degrees. This means the jet base is located very close to the rotation pole, offset by less than 8 degrees. Such a geometry has interesting implications. If the jet originates from a pocket of ice near one of the rotation poles, then that pocket would receive continuous sunlight as long as the rotation axis is aligned with the sunward direction. The pole would never rotate into shadow. The ice would sublimate continuously rather than intermittently. This could explain the persistence and intensity of the anti-tail jet. But why would the rotation axis be aligned with the Sun? At large distances from the Sun, where 3I-ATLAS spent most of its approach, the object would have had a nearly fixed orientation of its day side and night side. One hemisphere would face perpetual sunlight, while the other remained in perpetual darkness. This is because the apparent motion of the Sun across the comet's sky would be slow compared to the rotation period, especially at several astronomical units distance. For the jet to maintain its sunward orientation throughout the approach, the rotation axis of 3I-ATLAS would need to point approximately toward the Sun. The probability of such an alignment occurring randomly is about 0.5%, adding yet another low probability coincidence to the list. After perihelion, the situation becomes more complex. The gravitational deflection at perihelion altered the comet's trajectory by approximately 16 degrees. The Sun's direction relative to the comet shifted accordingly. If the rotation axis remained fixed in space, the alignment with the sunward direction should have been spoiled. Yet observations in December showed that the anti-tail jet persisted, still pointing approximately toward the Sun. This suggests either that the rotation axis shifted to track the Sun, which would require some torque mechanism, or that the jet emerged from a new source location after perihelion. Loeb noted this as an additional anomaly. Before perihelion, a jet base near one pole produced the anti-tail. After perihelion, a jet base near the opposite pole would be needed to maintain the sunward orientation. This requires two pockets of ice, located at opposite poles of the nucleus, both positioned close to the rotation axis, both capable of producing tightly collimated jets. Such a configuration is geometrically special. It represents another improbability layered on top of all the others. The alternative interpretations offered by mainstream planetary scientists focus on the complex physics of cometary outgassing. Jets are common features on active comets, and their orientations can be influenced by surface topography, inhomogeneous ice distribution, and shadowing effects. The apparent sunward direction might result from projection effects, or from the specific geometry of this particular comet's nucleus. Steve Desch of Arizona State University has argued that Loeb's calculations about 3I-ATLAS are fundamentally flawed because they neglect the role of solar radiation pressure on dust. According to Desch, the anti-tail can be explained by standard cometary physics without invoking exotic explanations. The dust in the tail responds to radiation pressure in ways that can create sunward features under certain conditions. The debate continues, with each side presenting models and analyses that support their interpretations. What is not in dispute is that 3I-ATLAS displays unusual jet activity that has attracted significant scientific attention. For observers following the comet through amateur telescopes, the anti-tail has been one of the most visually striking features. It gives 3I-ATLAS a distinctive appearance, different from the classic cometary form with a single tail streaming away from the Sun. Instead, the comet often appears to have multiple structures, a conventional dust tail, a plasma tail pointing away from the Sun along magnetic field lines, and the mysterious anti-tail pointing toward our star. Some images have shown the comet appearing almost to have spiral jets, reminiscent of the rotating beacon pattern seen in some active solar system comets. These spirals would result from the combination of rotation and outgassing, with the jet sweeping through space as the nucleus turns. The physics of cometary jets is genuinely complex, and many features that initially appear anomalous prove to have conventional explanations upon deeper analysis. 3I-ATLAS may ultimately join this category, its anti-tail explained by some combination of particle properties, viewing geometry, and outgassing dynamics that we simply had not encountered before. Or the anti-tail might represent something genuinely new, a behaviour we have never seen because we have never studied an interstellar comet as large and active as 3I-ATLAS. Objects from other stellar systems might have formed under different conditions, with different compositions and structures, leading to outgassing patterns that differ from those of solar system comets. Or, as Loeb continues to suggest, the anomalous features might point toward an artificial origin, technology masquerading as nature, a probe designed to look like a comet while doing things that comets should not do. The anti-tail is not proof of anything. It is a puzzle, a feature that demands explanation, a reminder that we do not yet fully understand what we are looking at. Whether the explanation proves mundane or extraordinary, the mystery has focused attention on the physics of cometary activity in ways that will benefit future research. When 3I-ATLAS has faded beyond detectability, the anti-tail will no longer be observable, but the images and data will remain available for future generations of scientists to analyse with techniques we have not yet developed. Perhaps someone, years from now, will look at the sunward jet of 3I-ATLAS and finally understand what caused material to flow in the direction it should not flow. Until then, the mystery persists. A jet pointing toward the sun, defying expectation, challenging explanation. One more anomaly in an object that seems determined to defy everything we thought we knew about visitors from the stars. Farewell to the visitor, Jupiter's hill, radius, and the final secret. And so we come to the end of our journey, though for 3I-ATLAS the journey continues. As you listen to these words, the interstellar visitor is already receding from Earth, its closest approach now behind it, its trajectory bending outward toward the cold darkness of the outer solar system. In the months ahead, it will cross the orbits of Mars, then the asteroid belt, then Jupiter, and eventually Pluto, before finally exiting our solar system entirely and resuming its eternal voyage through the galaxy. But before 3I-ATLAS vanishes into the void, it has one more encounter ahead. And it is an encounter that has generated more speculation, more controversy, and more statistical head-scratching than perhaps any other aspect of this remarkable object. On March 16th, 2026, 3I-ATLAS will make its closest approach to Jupiter. Jupiter is the giant of our solar system, a world so massive that it contains more matter than all the other planets combined. Its gravitational influence extends far into space, shaping the orbits of asteroids, capturing comets, and protecting the inner planets from some of the debris that would otherwise bombard them. The sphere of Jupiter's gravitational dominance is called its Hill radius, or Hill sphere. Within this region, objects can potentially be captured into orbit around the planet. Outside it, the Sun's gravity dominates, and objects follow heliocentric orbits. The Hill radius of Jupiter is approximately 53.5 million kilometres. When researchers projected the trajectory of 3I-ATLAS forward to the March 2026 encounter, they discovered something remarkable. The predicted closest approach distance to Jupiter was approximately 53.4 million kilometres, virtually identical to the Hill radius. The match is precise to within about 0.1%. In a solar system where Jupiter's orbit spans nearly 800 million kilometres in diameter, 3I-ATLAS appears set to thread the needle exactly at the boundary of the planet's gravitational sphere of influence. Loeb has calculated the probability of this coincidence at less than 0.004%, or about 1 in 25,000. Combined with all the other low-probability features of 3I-ATLAS, this alignment raises the total improbability to astronomical levels. What would it mean if this coincidence is not coincidental? The Hill radius has a special property. Objects at this distance from Jupiter are balanced between the gravitational pulls of Jupiter and the Sun. A spacecraft positioned at Jupiter's Hill radius would require minimal fuel for station keeping. Small nudges could maintain a stable orbit indefinitely. If 3I-ATLAS were to release material as it passed through this region, that material could potentially enter orbit around Jupiter. Particles ejected at just the right velocity could settle into stable positions near the Hill sphere boundary, particularly around the Lagrange points L1 and L2, where gravitational influences are balanced. Loeb has speculated that this might be the intent. If 3I-ATLAS is an artificial object, a probe sent by some other civilization to explore our solar system, Jupiter would be a logical target. The giant planet and its moons represent the most interesting destination in the outer solar system. Its moon Europa may harbour a subsurface ocean capable of supporting life. Its moon Ganymede is the largest satellite in the solar system. Its radiation environment, magnetic field and atmospheric dynamics make Jupiter a natural object of scientific curiosity for any technological civilization. Deploying observation platforms at Jupiter's Hill radius would allow long-term monitoring of the Jovian system without requiring continuous propulsion. Such platforms could study the planet and its moons for centuries, sending data back to their makers or simply accumulating observations for eventual retrieval. This is speculation, of course. There is no evidence that 3I-ATLAS will release anything at Jupiter, no evidence that it carries deployable technology, no evidence that it is anything other than a natural comet following a trajectory shaped by gravity and outgassing. The mainstream explanation for the Hill radius coincidence is simply that it is a coincidence. Extraordinary alignments happen occasionally. If we look at enough parameters of any object, we will find some that appear improbably fine-tuned. This is a form of selection bias, finding patterns after the fact that were never predicted beforehand. Moreover, the precise trajectory of 3I-ATLAS depends on parameters that are still uncertain. The non-gravitational acceleration has been difficult to model accurately, with different assumptions leading to different predictions. As observations continue, the predicted Jupiter encounter distance may shift, potentially moving away from the Hill radius and eliminating the apparent coincidence. We will know more in the coming months. Continued tracking of 3I-ATLAS will refine the trajectory, reducing uncertainties and clarifying whether the Hill radius alignment is real or a measurement artifact. The encounter itself will be observed by ground-based telescopes and potentially by spacecraft in the Jupiter system, including the Juno probe, which continues to orbit the giant planet. But whatever happens at Jupiter, it will not be the end of the story. 3I-ATLAS will continue outward, crossing the orbits of Saturn, Uranus and Neptune over the following years. By 2029, it will pass Pluto's orbit, finally exiting the region of space that we consider our solar system. And then it will continue falling through the galaxy, as it has fallen for billions of years before, as it will fall for billions of years to come. It will pass other stars, perhaps close enough to feel their warmth, perhaps not. It will accumulate more cosmic ray damage, more processing of its remaining ices, more layers of transformation from whatever it started as into whatever it will eventually become. If 3I-ATLAS survives as a coherent body, it will carry with it a record of its passage through our solar system. The volatiles it shed, the dust it released, the orbital perturbations it experienced, all of these will be encoded in its remaining structure. A future civilization, encountering 3I-ATLAS millions or billions of years from now, might be able to reconstruct something of its journey, might be able to determine that it once visited a yellow star with 8 planets, including a blue world teeming with life. What would they make of us? Would they find evidence of our existence in the residue left on 3I-ATLAS? Would they detect trace amounts of terrestrial dust caught in the comet's wake as it passed through the inner solar system? Would they wonder, as we wonder now, whether the visitor they are studying was natural or artificial? These are questions without answers, fantasies about a future too distant to contemplate. But they remind us that cosmic timescales dwarf human comprehension, that the story of 3I-ATLAS does not end when it leaves our observation, that we are witnessing merely one chapter in a journey that spans the age of the universe. Let us take stock of what we have learned. 3I-ATLAS is the third confirmed interstellar object detected by human astronomy, following Oumuamua in 2017 and Borisov in 2019. It is by far the largest and most active of the three, a genuine comet with a substantial nucleus, a well-developed coma, and prominent tails. Its origin lies somewhere in the Milky Way's thick disk population, around a star that was ancient when our sun was born. Statistical analyses suggest it may be 7 to 14 billion years old, potentially the oldest comet ever observed. The object displays numerous anomalies that have sparked intense scientific debate. Its trajectory is aligned with the ecliptic to an unlikely degree. Its arrival direction coincides with the WOW signal from 1977. Its chemical composition shows unusual nickel abundances. Its anti-tail defies easy explanation. Its non-gravitational acceleration may be fine-tuned to deliver it to Jupiter's Hill radius. Each anomaly might have a mundane explanation. Taken together, they present a pattern that some researchers find troubling, a constellation of improbabilities that seems too coherent to be random. The mainstream scientific community maintains that 3I-ATLAS is a natural comet, with exotic properties, unusual but not unprecedented, interesting but not alarming. The anomalies will eventually be explained by advances in our understanding of cometary physics and interstellar object populations. Avi Loeb and a smaller contingent of researchers argue that we should remain open to alternative hypotheses, including the possibility that 3I-ATLAS is an artificial object, a probe or beacon from another civilization. They do not claim certainty, only that the evidence warrants serious consideration rather than dismissal. The debate will continue long after 3I-ATLAS has faded from view. The data collected during its passage will be analysed and reanalysed for years to come. Future interstellar objects will be compared to 3I-ATLAS, providing a statistical context that is currently lacking. Eventually, we will have a better sense of whether this visitor was typical or exceptional, natural or anomalous. For now, we are left with wonder. An object from another star has passed through our corner of the galaxy. It has shed ancient ice into our sun's warmth, revealing chemistry from before our world existed. It has been photographed by rovers on Mars and telescopes in Earth, orbit and spacecraft en route to Jupiter's moons. It has generated controversy and excitement, and a renewed sense that the universe is stranger and more interesting than we sometimes allow ourselves to believe. Tonight, on December the 19th, 2025, 3I-ATLAS is at its closest to Earth. 168 million miles separate us from this messenger from the stars. That distance will only grow from here as the comet recedes and fades and eventually passes beyond our ability to follow. So let us say farewell. Farewell to the ancient wanderer, the 7-billion-year-old time capsule from the thick disk of our galaxy. Farewell to the anomaly generator, the object that made scientists argue and enthusiasts speculate, and everyone who looked up at the sky feel a little less alone in the cosmos. Farewell to 3I-ATLAS, wherever you came from, and whatever you are. May your journey be long, your secrets eventually revealed, and your passage through our tiny corner of space remembered by the species that watched you pass. We could not reach you. We could not land on you or sample you or follow you into the dark, but we saw you. We studied you. We argued about you. And for a few months in 2025, you made us look up and wonder. That is enough. That is more than enough. That is everything that science asks of the universe. The opportunity to observe, to question, to learn. Thank you for watching this special episode. Thank you for joining me on this journey through everything we have learned about 3I-ATLAS, from its discovery in July to its closest approach today. I hope you found the story as fascinating as I do, as full of mystery and possibility, and the beautiful uncertainty that makes science the greatest adventure humans have ever undertaken. If you enjoyed this documentary, please remember to like and subscribe. These actions help the channel grow and allow me to continue bringing you stories about the wonders of the universe. Hit that notification bell so you never miss an upload, and consider sharing this video with anyone you know who might appreciate a tale of cosmic visitors and unanswered questions. Tell me in the comments what you think about 3I-ATLAS. Is it a natural comet, an ancient wanderer from the galaxy's thick disk, remarkable but ultimately explicable by conventional science? Or do you sense something more in the accumulation of anomalies, something that hints at possibilities we have not yet dared to fully consider? I read every comment. I value your perspectives. This community of curious minds is what makes creating these documentaries worthwhile. A small disclaimer before we part. While I strive to present accurate scientific information, some of the hypotheses discussed in this documentary remain speculative and are not accepted by the mainstream scientific community. Science is a process of ongoing investigation, and our understanding of 3I-ATLAS will continue to evolve as new data becomes available. Always consult peer-reviewed sources for the most current and authoritative information. And now, as the night deepens and 3I-ATLAS begins its long farewell, let us carry with us the sense of wonder that this visitor has inspired. The universe sent us a gift from another star, a frozen time capsule from before our sun was born. We opened it as best we could with the tools available to us. What we found inside was beautiful and strange and full of questions we may never fully answer. That is the nature of exploration. That is the joy of discovery. And that is why we keep looking up. Good night, everyone. Sleep well, and may your dreams be full of stars.